Friends, welcome to Brave Solution Times. For today's video, we are going to see the proof of Theorem 1.5 and Theorem 1.6. So let's get into the video. Theorem 1.5, which is otherwise called as left cancellation law. Let A, B and C be square matrices of order n. If A is non-singular and AB is equal to AC, then B equal to C. Okay, so first they have given that A, B and C are a square matrix of order n, which means it can be 2 into 2 or 3 cross 3 matrix or 4 cross 4 matrix, and they don't know which in particular, so they have said that the matrix is of order n. And if A is a non-singular, and they are saying that A is a non-singular, so let's write it. A is non-singular, which means I have already said in my previous videos, if A is non-singular, then the condition is determinant of A is not equal to 0. So therefore you can say that A inverse exists. Okay, so you have to remember these three lines. If a particular matrix A is non-singular, then the determinant of that particular matrix will not be equal to 0, and then inverse of that particular matrix will exist. Okay, and then now we have to prove that now they have given an additional statement, which is AB is equal to AC. Then we have to prove that B equal to C. So I'll say an additional tip that why they are calling this theorem as left cancellation law. Here you can see that AB is equal to AC, so they have given this statement, and we have to prove B equal to C. So here there is a B and here there is a C. To the left side of the B there is an A which we need to cancel in order to prove B, and then for in the left side of C there is another A which we need to cancel in order to get our B equal to C, right? So if these two things are cancelled, we can get B equal to C. So this is why this theorem is called as left cancellation law. So since we have to cancel the left side values of B and C. Okay, so now let's we're taking AB is equal to AC, and we are going to prove B is equal to C. Okay, now here we have to cancel these two A, right? For that we are taking an inverse, we are multiplying inverse to the left hand side, which means we are pre-multiplying both sides by A inverse. So let's write it. Now let's multiply A inverse, so that we'll get A inverse into AB and then A inverse into AC. So why are we saying that pre-multiplies? Because we are multiplying A inverse before the values, right? Before AB it's A inverse, and before AC it's A inverse, right? So we are multiplying A inverse before the values. If we multiply A inverse after the value, we have to say post multiply. Okay, so this is the difference of pre-multiplying and post multiplying. So here we are doing pre-multiplying. So let's see this. Now here, in order to cancel A inverse and A, we already know that A inverse is nothing but 1 divided by A, and here there is another A, so that we can cancel this and we'll get an answer 1, so that 1 into B it will be B, so we'll get the answer. But maths doesn't work like that. For that, changing the brackets, we also have a property which is called an associative property. Using that property only, you can change the brackets. And by associative property, you can change the bracket so that it will be like A inverse into A. Bracket will change to these two, and there will be a B. And then here the bracket will be changed to this two, which is A inverse into A. And the answer is C. Okay, now you can see that A inverse A, B. Now you can cancel that A inverse and A, because 1 divided by A into A, it will be another 1. But again, maths doesn't work like that. Here again there will be a property for cancelling these A's. So that property is called property of inverse matrix. Property of inverse matrix. So according to this property, you can cancel these two elements, so that we'll get B, and here it will be a 1 again. So here we'll get an answer C. So therefore we got the answer B is equal to C, right? So this is easy, right? You have to just use some properties to define this. Now let's get into theorem 1.6. Theorem 1.6, and it is otherwise called right cancellation law. Let A, B and C be square matrices of order n if A is non-singular and BA is equal to CA, then B is equal C. Okay, so they have given that A, B and C be a square matrix. So it's a square matrix of order n, so that it can be 2 cross 2, 3 cross 3, 4 cross 4. So it can be anything, because so that they are saying simply as n. So the order is n, and there are 3 matrices here. And here, if A is a non-singular, so they have given the hint that A is non-singular. So if A is non-singular, I have already said that there are 2 conditions, that is, determinant of A is not equal to 0, and you have to write it as therefore A inverse exists. Okay, so these are the condition for if a matrix is non-singular. Then the next condition is BA is equal to CA, and then B equal to C. Now I'll give you some additional tip, that's why this theorem is called a right cancellation law. Here you can see that A is located to the right of B and C is located at the right of C. Sorry, A is located at the right of C, right? So here you have to cancel both the A in order to get B is equal to C, right? So you are cancelling the right side of the particular matrix B, so that this theorem is called as right cancellation law. Okay, now let's take the given part, which is BA is equal to CA. And now here we have to cancel this A, right? Now here we are going to post multiply A inverse on the both sides, because we have to cancel this A, so that we are going to post multiply both sides by A inverse. So I have already said that if we want to cancel something in the left hand side of that particular value, then you have to say that as pre-multiply. Now here we are multiplying A inverse to the right hand side of the B, which is after the value B, so that we are gonna say this as a post multiply. Now let's multiply 8BA into A inverse and CA into A inverse. So we are multiplying A inverse after this value, so that you are saying that as a post multiplication. Okay, now as I already said, we now need to change these brackets, right? So for changing this bracket, we are going to use a property called associative property. So therefore, by using associative property, you can change the brackets, which will get B into A inverse is equal to C into A inverse. And in order to cancel this A into A inverse, we can cancel directly, but we need to use a property for this, and the property name is property of inverse matrix. So we are going to use the property of inverse matrix. So therefore you can say that B into in the place of A into A inverse will get an answer 1, and then C, and here in the place of A into A inverse you'll get an answer 1. So that therefore B is equal to C. Therefore we have found what we have to prove. Then therefore you can say that as hence proved. Okay. So that's it for this video, guys. Thank you so much for watching, and if you enjoyed this video, please hit the like button and make sure to subscribe. See you in the next video. Bye.